We'll get started. We are now looking at what happens to the blade when the rotor is in hover, or for that matter, in vertical climb or vertical descent. Remember that the blade is a hinged structure, normally in the case of a hinged rotor at the root, so that it can flap up or down to alleviate the rolling moments at the hub, at the shaft, and also to alleviate some of the stresses. Therefore, the blade is going to want to move up because of the lift. But because it's a rotating structure, centrifugal force will push everything down, so it'll push the blade down. So the blade reaches an equilibrium position, so the angle that it assumes is called the coning angle. What happens if you don't have a hinge at the root? Many modern rotors are called hingeless rotors. So they have what they call a flex beam, which is like a rubber-like elastic structure, flexible structure. So this structure will bend upwards and coning the blade up or down. So think of it as a cantilever beam. So when you have a vertical lift load, the blade starts bending upwards or somewhat curving upwards. Because the root is flexible, it's able to cone upwards. So the objective is how do I find the coning angle? So that's what we're going to be looking at in this particular work. So let me see if I can get to my arrow. Okay, I'm going to switch over to the full screen mode. Well, we'll stay at this mode. I am not sure exactly how to go back to that particular mode. So let's see here. Okay, we'll continue. So as we talked about earlier, we'll continue. So let's see if I can advance my screen. Okay. So as we mentioned, blades are usually either hinged at the root or they have a flex beam, which is a flexible structure at the root. Later on, we'll show you some pictures of how the flex beam looks like, how the hinges look like, and so forth. So this is done to allow the blade to freely flap up and down without a huge bending load at the root. Of course, if you have a flex beam, you're going to have a bending moment at the root, but the blade will still be allowed to flap up and down. So the hinges in particular allow the blade to freely flap up and down. Aerodynamics forces are causing the blade to flap up. Centrifugal forces are causing the blade to flap down. So you reach an equilibrium angle or equilibrium position where the net moment of the hinge due to these opposing forces cancel out and go to zero. So that angle is called the coning angle. We're going to use a simple closed form expression. So we will assume that the blade is hinged right at the root. That means we're going to neglect the hinge offset. That's a small region near the root where you have all the shaft and all the other connectors. So usually the hinge is slightly outboard of r equal to 0, anywhere from 5% to 10% to 15%. But we are going to assume that the hinge is located at r equal to 0. Now, this is the coning angle, is the angle beta naught that we are trying to compute. Beta naught is a very small angle. So cosine of beta naught is 1. Sine of beta naught is just beta naught in terms of radian. We're talking about 4 to 10 degree of flapping angle, not more than that. So we're going to take a small radial location or a small blade element. That particular blade element produces some lift vertically upwards, but there's also a centrifugal force which is radially directed outwards. Remember, the centrifugal force will always push the mass away from the center, rotating center. Okay. So this is a very simplified model. Effect of hinge offsets are discussed in many other places in classical texts. And also Professor Prasad sometimes teaches a helicopter mechanics control, stability and control, where he talks about the effects of hinge offset. So let's look at the aerodynamic forces. So we have a small segment here of a width delta r at a radial location r. So it produces 1/2 rho times velocity squared, which is omega r squared, plus induced velocity squared, a lowercase v squared, times CL, which is a lift coefficient, times delta R is the lift produced by that particular lift element. Roughly, omega R is much larger than induced velocity V. So in these approximate calculations, V squared is neglected in comparison to omega R squared. So you get 1/2 rho C omega R, the whole thing squared, times CL times delta R. Now the momentum is R, okay, as shown in here. So the distance between the rotating axis and the lift is R times cosine of beta naught, which is roughly R. So if the moment caused by this lift force is R times dL, d capital L, therefore it will be 1/2 rho C omega R squared times, now if we pick up R, which is a momentum, times CL times dr. So what we have to do is integrate over the entire radius from root to tip, 0 to R, then you get this expression. If it was a numerical problem, more exact problem, you'll go from R equal to hinge to tip, which is capital R. And the CL will be computed by any number of ways, blade element momentum theory, or a actuated disk-based model theory, or a vortex theory based, or even a CFD based. Okay, however you compute the CL, lift coefficient, that's what you're using in here. So this is a moment at the hinge that's going to rotate the blade upwards, okay, flapping it upwards. Now let's look at the centrifugal force. Centrifugal force we know is mass times the velocity squared over r. The blade is spinning at an angular velocity of omega. So in-plane angular velocity is linear velocity is omega r. So that velocity squared divided by r times dm is a centrifugal force for a tiny strip. So if we simplify it, it will become omega squared times just r dm. So dm is the mass of the strips. So the mass can change because we may be using different structural element, different radial locations. They may weigh differently. So this force is acting horizontally, as we saw in here. Therefore, the momentum is not r cosine of beta naught, but it's r times sine of beta naught, which is the vertical distance between the original plane of rotation and the direction of the centrifugal force as shown in here. So r of sine of beta naught is just r times beta naught. So you multiply by r times beta naught as shown in here. Group everything together, you get omega squared r squared beta naught dm. When you integrate it, beta naught is a constant, so that comes out is a coning angle. Omega squared is a constant. Blade is spinning at a constant angular velocity in radians per second. So you get a r squared, radius squared, times mass integrated from root to tip or from the hinge to the tip. So that value is simply the moment of inertia of the blade, single blade. Okay. So it's I omega squared times beta naught. So equate the two, I omega squared times beta naught equal to the upward directed moment from the lift that we saw earlier. Now we can bring some of the components outside. 1/2 can be brought outside, rho may be brought outside. If you have a rectangular rotor or an equivalent chord length C, if you could bring it outside. If you assume CL is A times alpha, where A is a lift curve slope, so you bring A outside. And if you non-dimensionalize all the distances by the tip radius capital R, then the integral becomes 0 to 1 on the right-hand side of R over R whole cubed times integral of d of R over R. Alpha effective stays inside the integral, because alpha effective depends on theta, which may vary radially. It depends on the phi, which is a function of induced velocity, which may vary radially. Now this combination rho AC r power 4 over I is a non-dimensional number because beta naught is in radians, which is non-dimensional. Everything inside the integral is non-dimensional, including alpha effective in radians. So it follows that the log number rho AC r power 4 by I is a non-dimensional number. So log number is a structural property of the rotor. So if you have a very high log number, then you'll have a high coning angle and vice versa. Okay. So it's a measure of the balance between the aerodynamic effects and inertial effects. In general, log number is between 8 and 10 for articulated rotor. That means rotor that's got a flapping and lead lag hinge. It's got an effective value slightly less, between 5 and 7 for hingeless rotors with that elastic structural beam that kind of bends like a cantilever beam at the root. And we'll later look at the optimum values of log number, what happens when we lose power and so forth. Okay, so this is a closed form expression for coning angle. We could do more exact calculations if you keep rho inside, C inside, for a more general rotor, and if you integrate from the hinge to the tip. So this is the way we compute the coning angle of a rotor. So we stop this video at this point, and we'll continue with more information in a